Hey guys, so we are starting Cambridge International AS and A levels chemistry coursebook, and in this video we are going to cover self-assessment questions of chapter 8 Equilibria. Question number 16. Identify which reactants are acids and which reactants are bases in the following reactions. Part A, NH4 positive plus H2O is producing NH3 plus H3O positive. So to identify which is acid and base, we have to see proton donor and proton acceptor. We call H positive as proton, so the group which is giving this H positive or which is donating the proton is known as acid, and a group which is accepting H positive is known as base. So we have to identify only from the reactant side which group is donating H positive and which group is accepting H positive. Here the NH4 positive is changing from NH4 to NH3. It has one less hydrogen now. It has donated one proton. So it means NH4 positive will act as an acid here. H2O is changing into H3O positive in the product side. It means H2O is accepting a proton H positive and changing into H3O positive. So H2O will behave like a base here. Same way, we can check for the second reaction. In the second reaction, we have HCOOH plus HClO2 is reacting and producing HCOOH2 positive plus ClO2 negative. So again, here the HCOOH is changing into HCOOH2 positive. One extra proton is here. So HCOOH has accepted one proton when it is going to product. So it means this will behave like a base here. HClO2 is changing into ClO2 negative. Now it has less proton. This proton it has donated when it is going to product side. So it means it will behave like an acid here. So here is the solution. NH4 positive will be acid, H2O will be base in the first one, and in the second, HClO2 will act as an acid and HCOOH will act as a base here. Question 17. Identify the acid and base but on the right side of this equilibria. Right side means on the product side we have to see which one is acid and which one is base here. So to check from the product side, you have to first of all get an idea of conjugate acid and conjugate base pairs. Okay, if we for this reason we have to check the reactant first. Okay, we have to identify the acid and base from the left side first. Only then we can check the acid and base from the right side. Okay, so if we check out here, HClO2 is changing into ClO2 negative by donating one proton. It is giving one proton and changing into ClO2 negative. It means here HClO2 will be an acid here. Okay, it is behaving like an acid here. So when this HClO2 is behaving like an acid and changing into ClO2 negative on the product side, this ClO2 negative will be known as base. But this will be known as conjugate base. We call it conjugate base because it is produced from the acid. So this acid and this base is one pair here. Acid always produce base on the other side. Base will produce acid on the other side. Okay. So HClO2 is acid here and ClO2 negative is conjugate base here. Same way, we can check HCOOH is changing into HCOOH2 positive. When it is changing into HCOOH2 positive, in that case it is accepting one proton. It means HCOOH, because it can accept proton, it will be known as a base here. And after accepting proton, it is changing into product that will be known as conjugate acid. So it will be known as conjugate acid. So that's how we can easily identify the acid and base on the right side of the equation. And these acid bases will be known as conjugate acid and base. Okay, so we can check only if we know which thing is behaving like an acid and base on the reactant side. Same way, we can check for the second equation as well. And here will be the solution. Here the HCOOH2 positive is behaving like a conjugate acid and ClO2 negative is behaving like a conjugate base. So in the second, H2S is changing into HS. H2S is donating a proton here. So this one is acid here. When this one is acid, its pair HS will behave like a conjugate base. H2O is accepting a proton and changing into H3O positive. So H2O will behave like a base here. When it is behaving like a base, H3O positive will be conjugate acid of this base. So that's how we can easily identify conjugate acid and base on the right side of the equilibria. Question number 18. Nitric acid is a strong acid. Chloric acid, HClO, is a weak acid. Explain the difference between the strong acid and weak acid. So, actually, the strong and the weak acid has a difference in dissociation. Dissociation means breakdown of the acid. Strong acid can completely break down or dissociate in the equation, but weak acid will not completely dissociate. It will partially or somehow dissociate only, not completely. So that is actually the main difference between strong acid and weak acid. Here you need just definition. You can write strong acid completely ionize in water or dissociate in water, and weak acid will only slightly or partially ionize in water. So there are some other differences between the strong acid and weak acid that we have to use later in the question. So we are going to discuss here so that we can solve other parts of the question. So first difference is strong acid completely ionize and the weak acid slightly ionize. It means, what does mean by ionize here? Acid actually donate H positive as we just said. Okay. It means the strong acid will donate all H positive. Okay. It will donate H positive all. If it has one H positive in the formula, two, three, whatever, it will donate all H positive. Okay. Weak acid slightly ionize in the water. It means it is going to donate some H positive. Maybe one, maybe two, but it will donate only some H positive, not complete all H positive it will donate. Okay, it will donate some H positive. That is one difference. Then, because strong acid is donating all H positive, it means the complete acid will change into product. So it will be having a complete reaction. Reaction will go to completion here in case of the strong acid. When reaction is going to complete, no backward reaction is happening. It means we are going to write reactant here. We are going to write one sided arrow and then we are going to write product because it has a complete reaction. So reactants will go to the product and it will not come back. It will have only one sided irreversible reaction which will not be reversed here. Okay, then we can talk about the weak acid. Weak acid slightly dissociate. It will just donate some H positive and that H positive can again combine and go back. Okay, so first of all, it will not complete. The reaction will never go to completion. It will not complete. And if we talk about the arrow, it will be having always reversible arrow. It means we have reactant, it will change into product, and product can change back into reactant. And even it will support more backward reaction. Forward reaction will be very less here or slow here, and when it is coming backward, that will be more favorable reaction. It will be more fast and good here. So it means at the end we will be having more reactants, less product in case of the weak acid, because weak acid slightly dissociate and also come back. So backward reaction will also happen fastly. So weak acid will have more reactant as compared to product. But in case of the strong acid, we have more products, because all the reactants will change into product and no backward reaction is possible here. So these are some of the differences between the strong acid and weak acid. Okay, now we are moving to the part B. Write equation showing the ionization of these acid in water. We have to write the equation of the nitric acid so that it can behave like a strong acid, and we have to write the equation for chloric acid so that it can behave like a weak acid with water. Nitric acid has the formula HNO3. So HNO3 will dissociate HNO3 will dissociate with water. So HNO3 is a strong acid, so it will dissociate its proton to the H2O and makes H3O positive and NO3 negative as a product. And C, because it is a strong acid, so we are going to write only one-sided arrow here. Reaction will go to completion. Okay. And for the chloric acid HClO is a weak acid. It means slightly ionize. It will not completely ionize. So HClO will donate its proton to water, make ClO negative and H3O positive, and you can see irreversible reversible arrow here that this reaction is easily reversed. This reaction can also go back. So we have two-sided arrow here to show the weak acid dissociation. Okay, part C, suggest some pH values for the zero point 0.1 mole per dm cube aqueous solution of chloric acid and nitric acid. Chloric acid, as we already said, is a weak acid. So it will be having pH close to 7, near to 7, but it is not as diluted. It is just zero point 0.1 mole per dm cube diluted, a good concentration value it has. So it will be weak acid, but not so much close to 7, a little away from 7. So pH 3 to 5 is a pH for the weak acid for chloric acid. Nitric acid is behaving like a strong acid here, and strong acid has the pH close to 1 or near to 0 as well. So it will be having pH 1 or 2, both you can write. So that will be the pH for the strong acid. Part D, hydrazine N2H4 behave like a weak base. Write a chemical equation to show the equilibrium reaction of hydrazine with water. We have to write equilibrium expression of hydrazine with water. So hydrazine is a weak base. Okay. As we defined already about the strong acid and weak acid. Now I can tell you about strong base and weak base. Before solving the question, you have to write the difference between the strong base and weak base so that you can solve this question. So, strong base and weak base. Just like strong acid and weak acid, strong base can completely dissociate, completely ionize, and weak base will slightly ionize. That is the main difference here. Okay. Second difference is base actually do two things. Number one, base can accept H positive. Number two, base can donate OH negative. So base can have both properties. Some bases have the first property, they accept positive. Some bases have second property, they donate OH negative. So if we are talking about the strong base here, strong base means it will accept all H positive. Okay, it will accept all H positive, whatever is in the question. Whatever the acid is giving, it will accept all H positive from the acid. And strong base in case of the donation of OH means it will donate all OH negative. If it has one OH negative, it will donate one. If it has two, it will completely dissociate. It will donate all OH negative. So if it is accepting all H positive from the acid, or maybe it is giving all OH negative in the question, it means it is a strong base. The opposite will be for the weak base. Weak base can also accept H positive, but some, maybe one, maybe two, not all. Let's say the acid have the 2H positive, and we are reacting it with weak base, so weak base can accept maybe one, not complete two. Okay, so it will accept only some H positive. Okay, and in case of the OH negative, it can donate OH negative, but again it will donate some OH negative, not all OH negative present in the formula. Okay, so when we have again strong base, because it can accept all H positive or maybe it can donate all OH negative, so it will be having complete reaction. Complete reaction will be possible here. Okay, and in case of the weak base, reaction will not complete, just like the strong acid and weak acid. Reaction will not complete, and reaction can be backward as well. It will accept some H positive and again it can go back, because it will be a reversible reaction. And here it can donate OH negative some and also go back. So in case of the strong base, we will be writing again one-sided arrow, and in case of the weak base, we will be writing two-sided reversible arrow. So this is actually the main difference between the strong base and the weak base. So by using this concept, now we have to solve this part D. Okay, so in the part D, we have to write the hydrazine equation with water, and hydrazine is a weak base here. Okay, so hydrazine formula here is N2H4. N2H4 is reacting with water. Because it is a weak base, so we will be writing reversible arrow here. Now N2H4 has to behave like a weak base. Base means it has to accept proton from the water. Okay, it has to accept these hydrogens from the water. If it is accepting both hydrogens, it means it is a strong base. Right now, we have to write an expression N2H4 as a weak base. It means it will accept just one H positive from the water. So when it will accept one H positive from the water, it will make N2H5 now, because it has accepted one proton from the water. So and behaving like a weak base, so it will become N2H5 positive, and water after donating proton, it will become OH negative now. So that will be the equation for the hydrazine here. Here is the equation. Okay, state the relative concentration, high or low, for N2H4 molecule and for the product that we have written. Okay, see, as we already said that when we will be having reversible reaction, it can go back as well. So now we have to compare the concentration of N2H4 and product N2H5 positive. We have to tell at equilibrium which concentration will be present more, or overall in the reaction which will be present more, N2H4 or the product N2H5 positive. As this is reversible reaction, and we already said that in case of the weak base or in case of the weak acid, the backward reaction is more favorable. If backward is more, it means this product will be less here, its concentration will be less here, and N2H4 will be more here. Its concentration will be relatively more as compared to N2H5 positive. Question number 19. The pH of a solution depend on the hydrogen ions or the hydroxonium ions. Hydroxonium ions means H3O positive. We call H3O positive as hydroxonium ion, and hydrogen ion means H positive. So how many hydrogen ions or hydroxonium ions are present in anything, it will decide the pH, because pH is negative log of hydrogen or hydroxonium ions. Okay, so which concentration of ethanoic acid in this table has high concentration of hydrogen ion? So it is asking about the, first of all, ethanoic acid. Here is ethanoic acid. From the ethanoic acid, we have actually different concentration. Ethanoic acid at 1 mole per dm cube concentration has the pH 2.4. At zero point 0.1 mole per dm cube concentration, it has pH 2.9. And at 0.01 mole per dm cube concentration, it has pH 3.4. What does mean by this concentration? 1 mole per dm cube means it is actually a concentrated solution. We are making it little diluted. It will become zero point 0.1 mole per dm cube. Then we are making it more diluted, so it is becoming 0.01. When we are making it diluted, pH is also changing. 2.4 means a little strong acid. 2.9 means now a little less strong acid. 3.4 means now it is a little more weak acid. So we are weakening the acid by adding some water in it or by making dilution of this solution. Okay. So from these three solutions, from 1 mole per dm cube, zero point 0.1 and 0.01, we have to tell which concentration has highest hydrogen ions. So when we have 1 mole per dm cube means the concentrated solution or less dilution and also less pH. It means this solution here will have more concentration of hydrogen ions because it is 1 mole per dm cube and it is 2.4 pH. Okay. So 1 mole per dm cube ethanoic acid at pH 2.4 will have the highest hydrogen ions in all three ethanoic acids. Part B, check the same table and see which acid or alkali have highest concentration of hydroxide ions. Hydroxide ions means OH negative ions. So OH negative ions, alkali or the base most of the time have more OH negative ions. Okay, so it means we have to choose some alkali or base, not the acid. Okay, we have to choose from the table only alkali so that it can have the highest concentration of hydroxide ions. Okay, alkali or base. From the alkali or base, we have to choose the strong alkali or base because strong alkali or base will have more hydroxide ions. So it means we have here two alkalis or bases, sodium hydroxide and ammonia. So sodium hydroxide is actually a strong base and ammonia is a weak base. So we have to choose sodium hydroxide, not ammonia. Okay. Now we have to see sodium hydroxide can have 1 mole per dm cube concentration, zero point 0.1 mole per dm cube concentration, and 0.01 mole per dm cube concentration. 1 mole per dm cube concentration means it is more concentrated here. Okay. And also it has the highest pH as compared to others. So it will be the strongest base as compared to these two diluted one. So pH of 1 mole per dm cube solution is 14 and this sodium hydroxide at 1 mole per dm cube will be having highest concentration of hydroxide ions. So 1 mole per dm cube sodium hydroxide will be our answer here. Part C, explain why a solution zero point 0.1 mole per dm cube of ethanoic acid has low electrical conductivity when we compare it with same concentration of hydrochloric acid. So we are taking hydrochloric acid and we are taking ethanoic acid and we are taking their concentration zero point 0.1 and we are comparing them. We are saying that why ethanoic acid can conduct less electricity or conductivity as compared to hydrochloric acid of the same concentration. And the reason is electrical conductivity can be done only when we have hydrogen ions. Hydrogen ions are there in the solution. More hydrogen ions means more good electrical conductivity. Less hydrogen ion means low electrical conductivity. So hydrochloric acid is a strong acid and also you can check from the pH 1 and ethanoic acid is a weak acid for the same concentration having pH 2.9. So hydrochloric acid is strong acid, it will have more H positive. It means it will be a good conductor of electricity as compared to ethanoic acid. So same reason we can write here that conductivity depends upon the ions present in the solution. So few ions means less conductivity will be there. Part D, both hydrochloric acid and ethanoic acid can react with magnesium. So we are comparing hydrochloric acid strong and ethanoic acid which is a weak acid and we are saying both can react with magnesium, a metal. Rate of reaction of hydrochloric acid 1 mole per dm cube is faster as compared to the rate of reaction with ethanoic acid of same concentration. We have to explain why. Again, when hydrochloric acid and ethanoic acid are reacting with metal, magnesium, they are reacting with the help of ions present in the acid. So when we have strong acid, it will react more with more magnesium, and when we have weak acid, it will react less. Although the concentration is same, but strong acid will have more ions, it will react faster. Weak acid will have less ions, it will react slow as compared to strong acid. So same reason we can write hydrogen ion react with magnesium, and ethanoic acid has few hydrogen ions. It means it will be having slow reaction as compared to hydrochloric acid. Question number 20. There is a table given 8.11, and first of all we can discuss the table and then we will move toward the question. This table is giving you some dye names which can actually use as an indicator. Indicators are actually color dyes. So these are some color dyes that we can use as an indicator, and their colors at low pH are given. Just like methyl violet at low pH will be yellow, their colors at high pH value are also given. Their pH range are also given, that in between this pH range, this indicator can work. Okay, and their endpoint is also given, that maximum endpoint of pH we can achieve at which number. Okay, so this is the whole table that is given here. So our question is, which indicators tell those indicators that could be used for a strong acid and strong base titration? We have a strong acid and strong base, and we are doing its titration. And if you remember, in case of the titration, we react acid and base together, and for the color change we also use an indicator, because most of the time acid and bases are colorless. So to provide them color, we add some indicator, but not every indicator can work for every type of acid or base. We have to choose a specific indicator for the reaction. So for the strong acid and strong base titration, we have to tell which indicator from this table we can use. And in the part B, we have to tell which indicator we cannot use. Okay. So before choosing the indicator, first of all, we have to see how we can check. We can check by checking the pH range of this strong acid and strong base. We have to see what is the pH range of this strong acid and strong base, and then from the pH range of the indicator we can see which indicator is coming in the same range, because the indicator range and the acid base pH range should be same, only then indicator can work. Okay, so I'm telling this point again. First of all, we have to check the pH range of the strong acid and strong base. Then we have to check the indicator, which indicator is coming in the same pH range. Only that indicator can work. So now we are moving to how we can check the strong acid and strong base pH range. Actually, when we have the strong acid and strong base titration, we can just make a graph. First of all, let's say we have on x is the volume of any strong acid and strong base. We have the volume here, and on the y-axis we have the pH given. Strong acid means the graph will start from near 1. Okay, strong acid have the pH 1. Strong base means the graph will start from near 14, and when these two will start mixing, they will just meet at the center like this. And you have to see where they are giving you a sharp, straight line, a sharp fall here. It is going to fall, this line is going to fall and meeting this line. Okay. So we have to see which region here is giving you the sharp fall. So in between 10.5 here and 3.5 here, in between 10.5 and 3.5, it is giving us a very straight sharp line here. So that is the pH range for strong acid and base. So any indicator that is coming in between this pH range, that will come in between pH 3.5 and 10.5, can work for a strong acid and strong base titration. So now we can go to the table and we can see the indicators that are coming in this range. Okay, so if we check out the indicators, first of all, bromocresol green having the pH range in between 3.8 5.4, it can work because we have to check the indicator in between 3.5 and 10.5. So yes, it is in between 3.5 and 10.5. So 3.8 is more than 3.5 and 5.4 is less than 10.5. So it is in between the range. So it will work good. Then methyl red 4.2 to 6.3, it will also work as a good indicator for strong acid and strong base. Then bromothymol will also work good because it has the range 6 to 7.6. Then phenolphthalein will also behave like a good indicator for this, having pH 8.2 to 10. Okay, now if we check out bromophenol blue, bromophenol blue has the one range fine, 4.6 is fine, it is in between the range, but this lower range is less than 3.5. It means it can still work a little for as a indicator, but it will not be a good indicator. Okay, so same bromophenol blue, methyl orange and methyl yellow, all these three indicator has one side in the pH range, but their lower range is not in the exact range. It should be, their lower range is less than 3.5. So it means they will be indicator for the strong acid and strong base, but they will not be our first choice. Our first choice will be these four indicators here: bromocresol green, methyl red, bromothymol, and phenolphthalein, because they have the exact pH in between range. Okay, and these three will not be first choice indicator. And then which indicators that could not be used at all, and that is methyl violet. Methyl violet has the pH 0 to 1.6. It is not coming at all in the range, so it will not be used for the strong acid and strong base. And the second indicator is alizarin yellow. It has the pH 10.1 to 13. It will not be a good indicator. It is above the range. Okay. So these two indicators will not be good indicator. They will not be used for the strong acid and strong base. So that's how we can write that the bromocresol green, methyl red, bromothymol blue, and phenolphthalein are the suitable indicators. Methyl yellow, methyl orange, and bromophenol blue, they will not be first choice indicator because they are not coming in the exact range. Their lower limit is less than 3.5. And then methyl violet and alizarin yellow, these will not be used as an indicator because they are not coming at the steepest or the sharp line. Their pH is above the sharp line. Okay, question 21 is also related to the same table. It is saying that choose a suitable indicator that can be used for following titrations. We have 0.05 mole per dm cube nitric acid, and it is reacting with 0.05 mole per dm cube of aqueous ammonia. Here, the nitric acid is a strong acid and ammonia is a weak base. So now we have strong acid and weak base. So we have to, first of all, now the pH range will not be same. Now the pH range for the strong acid and weak base will be different. So first of all, we have to check the pH range. Then we can see which indicator will be a suitable indicator here. So for the strong acid and weak base, just like the nitric acid and ammonia, here is a graph. So strong acid means pH should be close to 1. So yeah, graph will start from 1. Weak base means pH should be less than 14. It should be more close to 7. Okay, so here is the weak base line. Okay, and if we check out their sharp line, straight line, their sharp line is coming in between here. It is coming in between 7.5 and 3.5. So the region sharp line pH range is 7.5 to 3.5. So whatever indicator is having exact range of 3.5 to 7.5, that will be good indicator for strong acid and weak base. And if you check out the table, The methyl red and bromothymol blue have the pH range in between 3.5 and 7.5. So these two will be the suitable indicator for strong acid and weak base. Part B. In the part B, we have aqueous sodium hydroxide and we have sulfuric acid. So sodium hydroxide is a strong base and sulfuric acid is a strong acid. So both are strong. We have already done this thing. When we have the strong acid and the strong base, the pH range is 3.5 to 10.5. So the four indicators we have already decided, all those four indicators will be good indicators for strong acid and strong base. Part 3. Now we have 0.005 mole per dm cube of aqueous potassium hydroxide and we have butanoic acid. Here the potassium hydroxide is a strong base and butanoic acid is a weak acid. So now we have strong base and weak acid. So first of all we have to find the pH range. Strong base means it will start from near 14. Weak acid means it will be near 7 now. It will not be near 1, it will be near 7 now. And if we check out the straight line at the center, it will be close to 14. It will be more towards the basic side now. Okay, so pH range is 7.5 to 3.5, where we are getting a steep, sharp line here. So any indicator in between 7.5 to 11 can work for this type of the titration. Such as the phenolphthalein, it is in between this range, so it will behave like a good indicator. Part B suggests why phenolphthalein is not a suitable indicator for finding the endpoint when we have hydrochloric acid and we titrate it with urea weak base. Hydrochloric acid means it is strong acid here. And urea, they are already telling us information, it is a weak base. So strong acid and weak base, we have to check its pH range and then we can see that the phenolphthalein is a good indicator or no. And what is the pH range of phenolphthalein? Okay. So when we have the strong acid and weak base, its pH range, we have already done this, it will be in between 3.5 to 7.5. So indicator should be in between 3.5 and 7.5. Phenolphthalein has a midpoint at pH 9, near to 9. So it is above this range, it is not in this range. So it means phenolphthalein is not a good indicator when we have strong acid and weak base. Question number 22. In this figure, we have a sketch graph which shows the change in pH when an acid and alkali react with being added slowly to the other. Both acid and alkali have concentration 0.1 mole per dm cube. Which of these statement is correct statement? So this graph is for weak alkali added into weak acid, strong alkali added into strong acid, strong acid added into weak alkali, or maybe strong alkali added into weak acid. So we can check the graph here. So see the graph, the upper line is close to 14 here. It means the base here is a strong base, or alkali is a strong alkali here. And if we check out this line is not close to 1, this line is more close to 7. So it means it is for the weak acid. So we have strong alkali being added to weak acid. So it will be D option. D will be correct answer here. So that's all about the self-assessment questions of chapter 8, Equilibria.